A second order differential equation is a differential equation with a second order derivative. So here we have a second order derivative. In this differential equation you can see that there's also a first order derivative. Now we will only deal with separable second order differential equations. Now what we will do is we will reduce this second order differential equation to a first order differential equation by making a simple transformation. So we replace dy dx with v, or whatever you want to call it. So we replace the first order derivative dy dx with v, and we rewrite this second order differential equation as a first order differential equation in v. So v is the first derivative. We can see that if we differentiate both sides of this, differentiate v with respect to x, well, v is going to be a function of x, because after all y is a function of x and dy dx will be a function of x. Okay, so we now differentiate the right hand side with respect to x. You know, we could write it down like this, the derivative of dy dx with respect to x, but of course we know that that's d2y, that's written d2y dx2. So we now rewrite our differential equation where v is the dependent variable. So the left hand side d2y dx2 is written dv dx, and the right hand side is 3 times v. So you see we get a first order separable differential equation. Okay, so let's solve this equation. We saw how to do this in a previous video. We bring all the v's to one side and all the x's to the other side. So we can divide both sides by v and multiply both sides by dx. Or if you like, that's the same thing as multiplying both sides by dx over v. Okay, if you stick dx over v in front of both sides, you will be able to separate this differential equation. So we have just v's on one side, x's on the other side. By the way, that 3 doesn't have to be there, of course. We could leave the 3 down here, it doesn't matter, it's just a constant. Next step is to integrate both sides. Now here we are essentially integrating 1 over v with respect to v. We know that that's ln of v. And we get our arbitrary constant, which we bring over to the other side. If we integrate 3 with respect to x, we get 3x. And we put our constant on the right hand side. Now before we go any further, we need to find out what this constant is. So this here is the general solution to this differential equation. We can find a particular solution to it by going to the boundary conditions. Remember, v is just dy dx. So I suppose I could write in ln of dy dx equals 3x plus c. dy dx is some function of x. You can stick x in brackets after, just to emphasize that dy dx is a function of x, if you like. Now if you go back up here, we see that dy dx equals 1 when x equals 0. So if you like, you know, another way to write this boundary condition is that dy dx at 0, dy dx is a function of 0, dy dx at x equals 0 is equal to 1. By the way, this is not the only boundary condition. You can see that there's another boundary condition that we will use when we are going from v, when we go to find y from v, when we get our eventual solution, but we have to take it in stages like this, so we need 2 boundary conditions because there are 2 integrations to be done here. Anyway, we're going to start with this boundary condition to find out what c is from our first integration. So we plug 0 in for x and we set dy dx equal to 1. So we plug 0 in for x here and we have to set dy dx equal to 1. So basically what we're doing here is we're getting dy dx at x equals 0, which we know is 1. So, well, we are given as 1. So now from this we can find out what c is. ln of 1 is actually 0, so you can see that we get 0 equals 0 plus c. So c is 0. So we can write down our particular solution to the differential equation. Ln of v is equal to 3x plus c, where c is 0. Of course, we set v equal to dy dx. If I go back up here, v equals dy dx. So now we can get another differential equation. So from this you see that ln of dy dx equals 3x. Okay, this is a first order differential equation. We need to separate the variables, but first of all, you know, we don't want this ln in front, so we raise e to the power of both sides. So if we put e to the power of the left hand side equal to e to the power of the right hand side, e to the power of ln of something is just that something. These effectively cancel, as we know. So we get dy dx on the left hand side. So e to the power of ln dy dx is dy dx, and the right hand side is e to the 3x. So now we can solve this differential equation to get y as a function of x. That's what we're aiming for. So what do? We separate the variables. This is very easy to separate them here. Multiply both sides by dx. And the next step is to put an integral sign in front of both sides. Integrating dy, we get y, and we get a constant, but of course, as we know, we bring that over. If we integrate 3x, we get 1/3 e to the 3x. Okay, if you integrate e to the power of a constant times x with respect to x, you get 1 over that constant times e to the constant times x. You can prove that using the chain rule. If you differentiate this with respect to x, you'll get back to this. Alright, so that's the case for e to the power of a constant times x. In this case, the constant is 3. I've nearly forgotten the arbitrary constant. Both sides, bring it over. I'll just write it here. Of course, this c is not the same as the c above here. If you want to make things precise, I suppose you could use a different letter, like d here. Alright, so this is a general solution of the original problem. To get the particular solution, we need to get d that satisfies the boundary condition. So as a reminder, I'll go back up here and note the boundary condition. Y is 0 when x is 0. We can summarize that by saying y at x equals 0 is 0. So if we go back down here, you know, just if you want to make it really clear, y at 0 is 0, that's what we're given, and we plug 0 in for x. So when x is 0, y is 0. 1/3 times e to the 0, well, that's 1/3 times 1, which is 1/3. So 0 is equal to 1/3 plus d. So this means that d is minus 1/3. So at last we can write down our particular solution. We just write this down, replacing d with minus 1/3. So this is the solution to our problem, and we're going to do a check of this. Okay, so let's take the left hand side of the differential equation. That's the second derivative of y with respect to x. So, well, you know, in order to get this, we have to get the first derivative. Okay, so we need to start by getting dy dx. We can't get the second derivative directly. So what's the first derivative? Well, we apply the chain rule. If we differentiate e to the 3x, we get e to the 3x back. But we must multiply by the derivative of the power, which is 3. And of course we have this 1/3 in front. Okay, so you leave the 1/3 to one side. Differentiating e to the 3x will give you 3e to the 3x. Differentiating minus 1/3 will give you 0. So this works out to be e to the 3x. Now, let's differentiate dy dx to get the second derivative. If we differentiate e to the 3x, we get 3e to the 3x. Okay, so that's the left hand side. Now let's look at the right hand side. So here's the right hand side of the differential equation. 3 times dy dx. But dy dx is e to the 3x, so we get 3e to the 3x. So these agree. The left hand side equals the right hand side. So that proves that we have a solution to the differential equation. We can very quickly check the boundary conditions. dy dx at x equals 0 should equal 1. Okay, so let's get dy dx at x equals 0. We can write it like this, or another way is to use a vertical line and write x equals 1. So dy dx is e to the 3x, so we get e to the 3 times 1, or e to the 3. I'm sorry, we want dy dx at x equals 0, of course. Okay, dy dx at x equals 0 is e to the 3 times 0. That's e to the 0, which is 1. So that does check out. We do get 1. Okay, and the second boundary condition is that y at x equals 0 should equal 0. So let's look at y. Well, sorry, here's y. So y at 0 is got by replacing x with 0. So we get 1/3 e to the 0 minus 1/3. Okay, which is 1/3 minus 1/3, which is 0. So that does check out. Show that if v equals ds dt, then d2s dt2 equals v times dv ds. Okay, so we're given this differential equation here. It's obviously a first order differential equation, and we want to transform it into a second order differential equation. That's an equation with a second derivative in it. It's easy to go from ds dt to d2s dt2. We just differentiate ds dt with respect to time. Okay, so we take this equation and differentiate both sides with respect to time. If we differentiate v with respect to time, of course we have dv dt. That's how we show that. And if we differentiate ds dt with respect to time, we get the second derivative of s with respect to time. Okay, so the trick now is to show that dv dt is equal to v times dv ds. Now, as you can see here, a context for this example is linear motion. You know, where v is the speed and s is the distance. But you know, we don't even have to think in terms of linear motion or any type of motion. You know, we could still transform this first order differential equation to this second order differential equation. So, okay, we've just differentiated both sides of this with respect to t, and we want to show that dv dt can be written as v times dv ds. Well, all we do is just fit it up, you know. We put a ds here because there's a ds in the denominator, and we need to compensate for this ds by writing ds in the numerator. You know, of course, we must make sure that we don't really change anything, that everything cancels back to dv dt, and that's the case. Now we look closely at this and see if it looks like v times dv ds. Well, we can just rearrange these around. This is not very rigorous, but it can be done. Okay, so we've dv over ds here, which is this here, and we have ds over dt. Well, if we look back here, ds over dt is just v. So we have ds dt times dv ds, or v times dv ds. So that's what we had to show. Hence, show that if d2s dt2 equals a, where a is a constant, given that ds dt is u and s equals 0 when t equals 0, then v squared equals u squared plus 2as. So now we're setting the second derivative equal to a constant a. Of course, this should ring a bell from the first video in this playlist where we discussed linear motion with uniform or constant acceleration a. S was the displacement, and the second derivative of s with respect to time is the acceleration. But even, you know, we could be just talking about general derivatives here. You know, we will still end up proving this result regardless of what s, a, v and u stand for. Now here we have an equation involving s and t, and we want to prove something that does not involve t. So we need to transform this differential equation using the previous result. So instead of d2s dt2, we will write v times dv ds, because this does not involve time. The independent variable here is s, not t. So in place of this second order derivative, we will write v times dv ds and set it equal to the constant a. Next we will solve this differential equation. The dependent variable here is v, so we are going to get v as a function of the independent variable s. So there are only two variables in this differential equation, v and s. A, remember, doesn't vary, it's constant. It's just a number. So hopefully we will find that the solution to it is given by this here. So v here is a function of s. The u is meant to be a constant, okay? U is actually ds dt at t equals 0. We could write it like this. The derivative at t equals 0, so it's just a number. So u is just a number. And a is just a number, well that's what we're given. S is the thing that varies, so v depends on s. So hopefully this thing will fall out of this differential equation. It'll be the solution to this differential equation. So here we have a separable first order differential equation. If we multiply both sides by ds, we get v dv equals a times ds. So the variables have been separated. We just have v's on the left hand side and s's on the right hand side. The next step, as we know, is to integrate both sides. Now integrating v with respect to v is straightforward. We just get a half v squared. Just add 1 onto the power and so on. Very straightforward. We get a constant of integration which is brought over and combined with the constant of integration on the right hand side. We're integrating a with respect to s. That's just the integral of a constant with respect to s. We just multiply the constant by s. And here's the arbitrary constant from both integrations. Now we need to apply the boundary conditions to find out what c is. So this thing here, as we said before, is a general solution of this differential equation up here, because we have a general number c, but we want a particular number c that fits these boundary conditions. Now t doesn't actually come into this equation here, as you can see, but when t is 0, that means at a particular time we want that ds dt is equal to u and that s is equal to 0. Well, ds dt, as we know, is just v. Okay, we saw that from the first part. V is ds dt. In other words, we want v to equal u and s to equal 0 at the same time. So we need to examine this equation at a particular time t equals 0, even though t is not a variable in this equation, obviously. But at a particular snapshot of time, we want v to be equal to u. So we put replace v with u, and we want s to be 0. To make it even clearer, we could think of both v and s as being functions of time, which they are actually, They depend on time, obviously. Well, we can think of v as being a function of s, of course, if we're just dealing with this equation. We don't involve t in it. But we haven't actually got v as a function of t, and we haven't got s as a function of t. But they are functions of time. Obviously, they depend on time, and if we let's set t equal to 0, we have v at 0, which is just u, and we have s at time 0, which we are told is 0. When t is 0, s is 0. S at time 0 is 0, and v at time 0 is 0. So now you see we know what c is. C is just a half u squared. We found c. So we take our general solution, this thing here, and replace c with a half u squared to get a particular solution. So we just copy out this. A half v squared equals a times s plus c, which is a half u squared. Multiply both sides by 2. V squared equals 2as plus u squared, or v squared equals u squared plus 2as, the familiar formula that we saw in the first part of the course for linear motion with constant acceleration. Now let's check the solution that we got. V squared equals u squared plus 2as. So here is the differential equation that we solved. So one way to check this would be to make v the subject first of all by getting the square root of the right hand side. Another way to check it would be to take it as it stands and use implicit differentiation when we get dvds. But I'll just do it this way. So here's our solution. We found v in terms of s. Okay, that's what we were aiming for, to find v as a function of s. Okay, the u and a are constants. Alright, so let's look at the left hand side of the differential equation. So the left hand side is v, which is this thing here. I could write it out, I suppose. I could actually just write v and see it more generally, but it doesn't matter. Here's v, and we must multiply by dvds, so we have to differentiate this thing with respect to s. So we have to use the chain rule, a half u squared plus 2as, then half minus 1 is minus a half, and we must multiply by the derivative of what's inside with respect to s. Now u is a constant, so the derivative of u with respect to s is 0. Here we have 2a times s to the power of 1, so when we differentiate this with respect to s, we get the constant in front of in front of s, which is 2a. Now notice what happens to the terms in the brackets. They give 1. Okay, so if you just add the powers, you get u squared plus 2as to the power of 0, which is 1. And we're left with a half times 2a. Well, that's just a. So that's equal to the right hand side. So that's our check. We could check our boundary conditions. At a particular time, v is u and s is 0. Well, that's very easy to check. You know, so if we plug 0 in for s, we should get v equals u. V squared equals u squared plus 2a by 0. So you can see that we get v squared equals u squared, or v equals u. Okay, so we got the familiar formula, v squared equals u squared plus 2as, by solving this differential equation. Now the solution of this one is covered in the previous video. That involves integrating the right hand side twice, and you know what we get? We get s equals ut plus a half at squared. So we wanted to find a function whose second derivative is a, and subject to these boundary conditions. So when t is naught, we want s to be naught.